Okay, let's look at chapter 6 now. I strongly recommend that if you look on Canvas in the lecture folder, there's an assignment, a review chapter 6, and the answer key is there also. I really recommend going through uh, that assignment so you know what I'm looking for with chapter 6. But the thing with chapter 6 is the first part of it, maybe the first third, is a little bit new, but it's fairly straightforward. The last part of it is all review of Gen Chem 2. So we're going to go through it real fast, and because there's so much review, and you should know it already, instead of notes, I'm just going to go through the book. I really don't have any notes on this chapter because I've got so many notes from Gen Chem 2. But we're just going to go through the book to highlight what we're looking at here because a number of these concepts you should know already, and we're going to use them for organic reactions. All right, a few things to get out of the way. I guess I just put it in this chapter because I didn't know what to do with it. When you write organic reactions, there's a couple ways you can write them. But what we're going to find is we're going to have a reactant and we're going to want to make a product, and sometimes it takes more than one step. But I don't want to say this goes to this product and then that product goes to this one, then that product goes to this one. Writing everything down multiple times is redundant. So the way we're going to write it is this. If we take this reactant here and we're going to put one CH3MgBr, which means the first reaction we did was we took this molecule here, this is acetone, added this methyl magnesium bromide to it, and got a product. And after we got that product, after that reaction was done, we then added water to the reaction mixture, and after adding water, then we get this product right here. And the other thing we do, because we're not so much worried about the other byproducts, we're just worried about what happened to the organic molecule, we tend to just write the organic product, and we don't really worry about the inorganic or the byproduct that we don't care about. Because what we did here was change this ketone into a tertiary alcohol, and that was the important part of this reaction. All right, note that we also didn't have to write this acetone plus CH3MgBr. We could just write it over the arrow, which means if we go down here, if we have this reaction down here, there's really two ways to write it. We could write this cyclohexene plus Br2 goes to this molecule, or we could put cyclohexane, just the Br2 over the arrows going to the product molecule. And a lot of times we want to indicate other things that we need. So if you see something like a cyclohexane, Br2, heat or light, we're going to find out that means radical conditions, and CCl4 is the solvent. Question, how did you know that all of this was mixed together? You had the bromine, heat and light, and CCl4. How did you know that CCl4 wasn't like the second reagent or a second reactant that we put in there after the first reaction was over? Well, you know it's not, because there's not a 1 or 2. If there's a 1 or 2, that means we did one thing first, and then when it was done, did the second part. This is all together, so if you see the CCl4, okay, that must be the solvent that's in there. Okay. Now let's look at the kinds of organic reactions that we're going to be looking at. The first is a substitution reaction. In the next chapter, chapter 7, is all about substitution reactions. Very straightforward. You have an organic molecule with some group on it. They call it Z here. And you react it with some group Y, and Y substitutes for Z. Z was on there. You react it with Y. Now Y is on the organic molecule, and Z just substituted Z for Y right here. All right, and here's some examples. If you have an iodine and a chlorine here, you can just substitute those off. All right, the next type of reaction in chapter 8 is elimination reactions. Here you have a molecule that has an X and a Y that are one bond, or technically three bonds apart. X is bonded to this carbon, one bond. This carbon is bonded to another carbon, two bonds. That carbon is bonded to Y, three bonds. So X and Y are on two different carbons, but those carbons have to be adjacent to each other. This is elimination, where the X and Y are now gone. They've been eliminated, and a pi bond is formed. So elimination reactions form pi bonds. If you can get an X on something on one carbon to leave with something else on another adjacent carbon, you'll form a pi bond. You can take an alkane to make an alkene, or an alkene to make an alkyne with this type of reaction. And here's an example. We'll go through loss of HBr. If you have hydrogen on one atom, carbon atom, and the adjacent carbon atom has a bromine, throw in some base and you can do this elimination reaction. Okay. The opposite of elimination reactions are addition reactions. With addition reactions, we have a pi bond and you add the X and Y to it. So it's literally the opposite step from elimination. These are addition reactions. And here's some examples there. Let's see. And those are the main type of reactions we're going to look at, including our acid-base reactions that we talked about in Chapter 2. That makes up the bulk of organic reactions: addition, elimination, substitution, acid-base. All right, now let's look at bond breaking and bond making, and we're getting closer to stuff that we've already heard before. When reactions occur, we've talked about the reaction mechanism, the detailed description about how bonds are broken and how they form. I like to call it what hits what when, which molecules smack into what other molecules, what bonds get broken, then what bonds get formed. And that's the mechanism of a reaction. You should remember that term from Gen Chem 2. The kinetics chapter was all about mechanisms. And the first thing we're going to talk about is bond breaking. Now, bond breaking is always endothermic. It always takes energy to break a bond. You have to add energy to get bonds to break. There are two ways bonds could break. One is by homolysis or homolytic cleavage, where if you have A bonded to B, A gets one of the electrons in the bond and B gets the other electron in the bond. So remember, a bond is two electrons. One electron goes to A, the other electron goes to B. That's homolytic bond cleavage, and it's actually kind of rare. We will cover this in Chapter 15, and that's really the only, you don't see it that often. Most of bond breaking is heterolytic, because usually one of the atoms is more electronegative than the other for this AB bond right here. And the more electronegative atom is going to take both electrons from the bond. So this bond between A and B has two electrons. Both of the electrons go on atom B. Or they could both go on atom A, whichever is more electronegative. And so with atom B taking both electrons, it becomes negatively charged. Atom A, since the electrons were taken away from it, becomes positively charged. So these are often called ionic reactions when we do this homolytic or this heterolytic bond cleavage here. These are ionic reactions because we tend to form negative ions and positive ions when we run these reactions. All right. And note, bond breaking always takes energy. When you break the bonds this way, we have a special way to indicate it with certain types of arrows. And there we go. If you do homolysis, a homolytic bond breaking, that means we're going to say, okay, we're going to draw an arrow from the bond to atom Z, but if you look closely at this arrow in your book, you'll see that it's a one-sided arrow. Let's do a crash zoom here. You see, focus this crash zoom. You'll see that the arrow just has one point, just one little barb on the tip of the arrow right there. The same thing over here, only one barb on the arrow when you break the bond homolytically with one electron going to Z, the other electron going to this carbon. Note, if you do it heterolytically, where both electrons go onto atom Z, our arrow is going to have two barbs on it, a normal type arrow. All right. you do note our homolytic bond breaking, you get a radical, because when you have just one electron on a carbon atom or on Z, an unpaired electron, we call those radicals. When you do heterolytic bond cleavage, you can get a carbocation if both electrons go to Z. If both electrons go onto the carbon, you get a carbanion. And the next page in your book just has this nice little table showing radicals versus carbocation versus carbanion and what they look like. Where you've got the lone electron here, positive charge carbocation, negative charge with its two electrons, carbanion. So bond breaking always requires energy. It takes energy to break the bond. Bond making, bond formation, always releases energy. Bond formation is always exothermic. So here's two ways to make a bond. If you have two radicals, they could come together. This electron on B and this electron on A get together to form this bond. And as we said before, these types of reactions are fairly rare. You have to really set up the proper conditions for this. Most of our reactions, the negative charged B, or the electrons on one, both electrons on one reagent, attack the positive other reagent to form the bond, and so this bond between A and B came from both electrons on B. All right, you may realize when we look at this, this is how most of our organic reactions are going to be. Note, B is an electron pair donor, A is an electron pair acceptor, which if you remember your definition, that means B is a Lewis base and A is a Lewis acid. So it turns out, except for these types of radical reactions here, most organic chemistry reactions are Lewis acid-base reactions. And that'll become very important in the next chapter. All right, and if we take a look at the arrows that we draw in organic chemistry, here's a table that sums them up. We have our normal reaction arrow. This is the one we tend to draw most of the time. Now, a lot of people like the equilibrium arrows because that's the reality of the situation. It turns out most reactions are actually equilibrium, whereas we can push them to the right using Le Chatelier's principle. Most reactions are equilibrium reactions. Because of that, we know they're equilibrium. We know the reactions are reversible. We tend to just write the regular arrow instead of the equilibrium arrows, just because it takes twice as long to draw two arrows compared to one. Right. Never confuse equilibrium arrows with resonance. Remember, this is a resonance structure arrow. And we've talked about our double-headed barb. Our normal curved arrow shows us our flow of electrons, and the half arrow shows the flow of one electron. The double arrow shows the flow of two electrons. So when we look at examples here, here's an example of a reaction where this H2O plus here breaks off. This bond breaks. Both electrons go on this oxygen. Note this oxygen had one lone pair. It gains another lone pair from these two bonding electrons. So now the oxygen has two lone pairs on it. And we've got a carbocation because this carbon had four bonds. Now it only has three. And the oxygen took both electrons. And that's how the arrows work. And we're going to see some reactions have a number of arrows. Look at all that happens in this reaction. This tells us that a lone pair on hydroxide is going to form a bond with hydrogen, because whenever you have a lone pair at one end of the arrow and the point is pointed to an atom, that means a bond forms there. So the hydroxide, a lone pair on hydroxide, forms a bond with this hydrogen. Whenever you have an arrow from a bond to another bond, means that the two electrons of this bond, this carbon-hydrogen bond, then become two electrons on this carbon-carbon bond. The two electrons go from here to here, and we form a double bond. And then this chloride takes those two electrons with it. It had three lone pairs. Now it has four lone pairs. So we call this pushing electrons, and that's the big thing with organic chemistry, is pushing the electrons, showing where all the electrons go when reactions happen. And that's our mechanism. That shows us the mechanism of the reaction. what hits what when, how the reactions occur. All right. The last part of this video is good news and bad news. It is bond association energy. All right, we're getting in topics like delta H, remember, enthalpies, heats of reactions, exothermic, endothermic. And note, bond breaking is always endothermic. It always takes energy to break the bond. You get some of that energy back when you make the bond, because bond making is always exothermic. Now, whether the overall reaction is endothermic or exothermic depends on how much energy did you have to add to break the bonds compared to how much energy did you get back when the bonds formed. If the bonds that get formed are more stable, lower in energy than the bonds that got broken, that means it took less energy to break the bonds. You got more energy back when you made the bonds, and the overall reaction is exothermic. If the exothermic bond making part is more energetic, has more energy involved than the endothermic bond breaking part. And recall, when delta H is positive, that means that overall the energy is absorbed, it's an endothermic reaction. When delta H is negative, it's an exothermic reaction. And so if you really want to get a good handle on why the reactions we're going to discuss throughout the rest of the book happen, just memorize this table. The bond association energies of some common bonds. If you knew how much energy it took to break and thus make some bonds, that can tell you what happens in our reactions. So the better you understand this table, the better you'll understand organic chemistry. However, what we're going to do, because I don't want to memorize this table, I do not have this table memorized, we are just going to memorize the trends. For example, if we just take a look right over here at halogens, the carbon-fluorine bond versus the carbon-chlorine, carbon-bromine, and carbon-iodine bond, we see that the bond energy gets lower and lower, which means these are weaker bonds, which the carbon-iodine bond is a weaker bond than the carbon-bromine bond, and the carbon-bromine is weaker than the carbon-chlorine bond, which is quite a bit weaker than the carbon-fluorine bond. So what that tells us is with our halogens, if you're going to break off a halogen, it's easier to break off a bromine than a chlorine off of a carbon, because this is how much energy it takes to break the bond. All right. So when we get through the rest of these chapters, we're just going to memorize these trends. We're not going to memorize these numbers. We're just going to be looking at the trends that happen with these molecules. And we'll have various rules that we will look at to look at these trends. And what happens is people just memorize the rules and they forget, wait, why is this? Why does the chlorine break off? Why does the bromine break off easier than the chlorine? It all comes back to the bond association energy. It's a weaker bond. But the good news is you do not have to memorize this table, because in the upcoming chapters we will memorize the trends that we need to memorize for this. Okay, that's enough for this. We're next going to look at thermodynamics equations, and we've covered the rest, almost all the rest. Yes, all the rest of this chapter is essentially a review of the kinetics and the thermodynamics chapter of Gen Chem 2. So you should know this stuff.